Right now, a machine built 47 years ago, before smartphones, GPS, or the internet even existed, is flying alone more than 24 billion kilometers away from Earth. And somehow, this machine is still talking to us. In the 1960s, if NASA wanted a close look at Jupiter, Saturn, Uranus, and Neptune, they faced a massive logistical wall. Visiting all four giants meant building and launching four distinct multi-billion-dollar rockets, a process that would have consumed decades of time and funding. Then, an engineer named Gary Flandreau noticed something hidden in the orbital math. By the late 1970s, the four outer planets would arrange themselves into a sweeping curve. This cosmic shortcut allowed a single spacecraft to visit them all. But this alignment happens once every 175 years. Miss the 1977 window, and the next chance is 2152. They had an absolute deadline. The problem was, Neptune is 4.5 billion kilometers away. Nobody on Earth possessed a rocket with nearly enough fuel to fly a machine that far in a straight line. To bridge that impossible distance, they used a physics exploit called a gravity assist, or the slingshot effect. Instead of trying to carry all their fuel, they aimed the spacecraft slightly to the side of a massive planet. As the craft falls into the planet's gravitational well, it gets pulled along with the planet's momentum. If the approach angle is precise, the spacecraft doesn't get trapped in orbit. It steals a tiny fraction of the planet's orbital energy, whipping out the other side at a massively accelerated speed. Voyager essentially hitchhiked. It used a speed boost from Jupiter to reach Saturn, and then grabbed another from Saturn to keep going. By chaining these slingshots together, it achieved a velocity so extreme that the sun's gravity can no longer pull it back. Speed was solved, but survival in deep space requires electricity. Standard solar panels work near Earth, but by the time you reach Jupiter, sunlight is 25 times weaker. Out at Saturn, it drops by a factor of 90. In that kind of cold darkness, solar panels are useless. So NASA installed a radioisotope thermoelectric generator, or RTG. This is a nuclear battery. It's packed with plutonium-238, a radioactive material. As the plutonium atoms naturally break down and decay, they generate steady heat, which the RTG continuously converts into electricity. But look at this chart tracking the spacecraft's power supply since 1977. Because the plutonium is constantly decaying, the available power permanently drops. Voyager launched with 470 watts of power. Today, it's surviving on barely 250. To counter this starvation, modern engineers on Earth are playing a slow game of triage. They are systematically turning off Voyager's heaters and scientific sensors one by one, sacrificing its ability to observe the universe just to keep its core communication lines open. And that communication system is barely a whisper. When Voyager sends a signal home, it transmits at just 23 watts. That is less power than the tiny light bulb sitting inside your kitchen refrigerator. To catch a signal that weak from billions of kilometers away, NASA relies on the Deep Space Network. These are colossal, 70-meter-wide antenna dishes, sensitive enough to capture a distant transmission. It takes over 22 hours traveling at the speed of light just to reach us. By stealing momentum from gas giants, capturing the heat of decaying atoms, building massive mechanical ears on Earth, scientists pushed a piece of 1970s hardware out of the solar system entirely. In March 1979, before it left the neighborhood, Voyager made its first major pass at Jupiter. The scale of this planet is difficult to comprehend. If it were hollow, you could fit 1,300 Earths inside of it. Astronomers had observed Jupiter through telescopes for centuries, but Voyager returned the first detailed close-ups. It exposed the Great Red Spot, a colossal, churning storm large enough to swallow 2 entire Earths. Because Jupiter is entirely gas and has no solid landmass to break the winds, this single storm has been raging continuously for at least 350 years. These images showed that gas giants were not static, quiet spheres floating in the dark. They are violently active weather systems surrounded by faint, dusty rings. The most startling observations happened on Jupiter's moons, driven by a mechanism called tidal heating. Because Jupiter's gravity is so intense, it physically stretches and squeezes the solid moons orbiting it. This constant flexing acts like a vice, generating massive amounts of internal friction and heat. On a moon named Io, that tidal heating pushes molten rock straight through the crust. Voyager captured active volcanoes erupting in real time. It was the first time humanity had ever seen active volcanism anywhere outside of Earth. The heat does something entirely different on a neighboring moon called Europa. Voyager photographed thousands of deep fractures across Europa's icy shell, revealing the clear patterns of a vast liquid water ocean being kept warm deep beneath the frozen surface. Wherever we find liquid water, we find the potential for biology. By exposing that hidden ocean, Voyager elevated a tiny frozen moon into the single most promising location for discovering alien life in the solar system. Right now, the clock on Voyager is running out. Current estimates suggest that somewhere between 2028 and 2030, the nuclear battery will degrade past the point of basic function. That 23-watt signal will stop, and the spacecraft will go permanently dark. But it carries one piece of analog cargo. Bolted to its exterior is the golden record, a 12-inch copper disc containing 150 images, the sounds of wind and rain, greetings in 55 languages, and the biological blueprints of the human race. The engineers who calculated that 175-year orbital window knew they were building a machine that would outlast their own connection to it. Long after it loses power, this 825-kilogram block of metal will continue its quiet drift through the Milky Way, humanity's most distant, permanent footprint.